So I would like to give an overview or a basic introduction to the field of runtime verification. We have heard quite a lot about runtime verification this morning. So we had an introduction by Adrian, and then we had an application field in the area of cyber-physical systems. And the previous talk by Wolfgang, we were using certain runtime verification checks based on JML, which is close to the area of runtime verification, but but perhaps not really the main idea of runtime verification. For those of you that are experienced in the field, you have seen this presentation before, so might be a little bit boring, but it may also be a good repetition anyway. So it's mostly intended as an introductory course. So what is runtime verification? Well, the idea is that we have a system, let's say, like in this example, it consists of 4 components. They are interacting somehow. It could be 4 individual components sending messages. Let's say in this case, it's like S1 is sending a message to S3, and we are kind of monitoring such message exchange. But it could also be the call graph of some functions in let's say, in some Java code. And the idea of runtime verification is that we attach a monitor it, and the monitor basically observe that, for example, the message exchange going on here is correct according to some certain high-level specification. So the idea is not that we program. Okay, I'll restart with new power. So the idea is that we attach a monitor to the system, and the monitor is actually synthesized from some high-level specifications. The idea is that we don't program Java code or something like that ourselves, but that we try to understand what really has the system to hold, which kind of properties does the system has to satisfy, and we don't want to deal with the problem of implementing or writing code following such a property. We want to synthesize it from some high-level specification language. So as Adrian pointed out, it's a verification property. It verifies partially the correctness property at hand, but it's based on the actual execution. It's not like model checking where we consider all possible executions, but we really run the system and consider a single execution. So it's a simple verification technique in 2 respects. First of all, it is not so it's not a heavyweight verification technique. It doesn't consume so much resources, and it's also easy to understand in some sense. It's complementing existing verification techniques like model checking and testing. Formally, we solve the word problem. So we have an execution. An execution is a linear sequence of something, let's say the events that the system emits, or let's say we have access to the states of the system, so it's a sequence of the assignments to variables, something like that. But formally, it's a word, right? And the question is, so we have a specification, let's say phi. Phi describes the correctness property, and it defines a language. Well, it defines the language of all executions, the language of all words that satisfy this property. And the word that we're looking at, this W, should be among those. It should satisfy the property, so it should be in the language that satisfies our correctness property. We will change it a little bit, this definition, but in essence, it's a word problem that we're going to solve. Right. What is model checking? Model checking, well, we have a specification as well. For example, also in linear temporal logic, one of the temporal logics that are used in this area, we also define in that way a set of runs that are correct according to our specification. So we define the language L of phi, and we have a system or a model of the system, an abstraction of the system, typically a kind of transition system. You learned about transition systems this morning if you don't know them. And the question is, does all run satisfy the specification? In other words, is the set of executions of our system among those that are allowed? So we answer the subset problem. All right, model checking is typically done on infinite words. We consider something like models for a web service or something like that. While runtime verification, we deal with finite words because we analyze the current execution, and it's too time consuming to consider an infinite execution. But we follow typically in the area of online runtime verification, the execution of the system. So the execution is growing step by step. And while the system is executing, we want to get a verdict whether the system satisfies the specification, whether it does not specify the specification, or whether we don't know yet, something like that. In runtime verification, the complexity, that is the main criterion for improving runtime verification techniques, is the overhead of the monitor. Yeah, that is what Wolfgang also mentioned is true in the field of JML. While in model checking, the overall verification problem is the means of complexity. In model checking, we need to understand the system, we have to analyze the system, so we need the code, while we can use runtime verification also for black box systems. On the other end of verification techniques, we have testing. It's an incomplete verification technique. The test cases are typically a finite sequence of input and output actions. And, well, let's forget about that. But what does it have to do with runtime verification? Not really a lot, but there is a second form of testing, which is called oracle-based testing. So where we have test cases that are only sequences of inputs, but we have a so-called test oracle, that is what is called there, or what it would be called in the setting of runtime verification, a monitor that checks whether certain problems occur when executing the test cases. So this is basically what we do in runtime verification as well, but from the research point of view, we have different kind of questions that we are going to answer. Well, in testing, typically the oracle is done manually. You write some Java code or whatever, Python code, something like that, while we want to synthesize the monitor from high-level specification languages. And in this example, or in this course, I take LTL as a specification language, but at the end, or what you learned this morning already, LTL is limited for these kind of applications because we are not talking about interesting extensions of runtime verification techniques like how to deal with data, how to deal with distributed systems and all kind of that stuff. When you look at research papers, if you want to publish papers on testing, then one of the goals is how to find good test suites, how can I generate test cases generate covering a large part of the system and so on. While in runtime verification, we work on how to design new specification languages, extensions of LTL in some way or the other, how to synthesize efficient monitors, either running in parallel to the software on the same hardware, or what we do right now in Lubeck quite a lot is to execute the monitors on additional hardware, not influencing the execution of the system that we're going to observe. All right, so that's the plan for the next 2 hours. So we talk about runtime verification for LTL, and we consider different semantics. And at some point, we will come to the question how to build monitors. We also discuss the notion of monitor properties, which is slightly different to what Adrian discussed this morning. Sorry. And then I will stop with a few small extensions. And perhaps I'm also a little faster than 2 hours, but we'll see. So, a definition, we all need a definition. Runtime verification is the discipline of computer science that deals with the, and so on. So what do? Basically, we look at the system, we want to observe the runs of the system, we want to synthesize monitors from specifications. All right. What is a monitor? A monitor is a device that reads a finite trace and yields a certain verdict. A verdict is something from a truth domain. Yes? One hour, okay. Now, but I see, I see. Yeah, we'll see what the monitor does. All right, so runtime verification is a very big field. We have lots of different questions. We can study finite traces, we can study finite non-completed traces that are actually prefixes of infinite words. How do we integrate the monitor to our system? Do we integrate it inline? Do we merge it to the actual code of the system? Or is it a separate program not directly affecting, for example, the memory space of the system? When do we monitor? Do we monitor online while the system is executed? Do we monitor offline? We have stored the trace, and later on, let's say in some database, and later on we analyze the system, the trace. Does our monitoring interfere with the underlying system? Yeah, so the example, or what Wolfgang said in his previous presentation at the end, JML monitors and runtime assertion checking slows down the program, but it also changes the program. So it can happen that the program is correct when the monitors are in the program. If you remove them, they're wrong. Yeah, so it's always good not to be invasive with the monitoring stuff. Do we only want to observe the system, or do we want to steer the system? What are we actually monitoring? Are we monitoring event sequences? Are we monitoring state sequences, the input-output behavior? All these kind of parameters change the actual runtime verification algorithm that is underlying. Where do we apply it? Do we only apply it for, let's say, safety checking, or do we apply it for security checking? Well, how do we apply it for security checking? I don't know, but I hope that we'll learn something on Wednesday about security checking, and in some additional workshop eventually taking place in Sicily, Gerardo. All right, what do we do today? So we talk about finite non-completed words as prefixes of infinite words. We only talk about, we don't care about online, offline stuff and so on. Only for this kind of stuff we generate monitors that somehow may be executed to check the underlying system. I don't talk about that. I only talk about the different way of semantics given to finite words. All right, so let's start with runtime verification for LTL. So what is LTL? So we want to observe a trace. A trace is something like that. It's maybe finite. Maybe it's not so finite because it continues over there, but you don't see it. So you want to reason about the shape of this kind of path. How can you do that? Well, we can do that, for example, using a temporal logic, something like LTL. I'm not paid for this presentation here, so I have to get something out of that. I have to make a few commercials in between. One commercial is, for example, don't just use LTL, but use regular LTL. If you don't know what regular LTL is, Google for it. It's cool. Anyway, so what is LTL if you don't know it? Well, we have constants, true and false. We have atomic propositions. We have disjunction, and we have conjunction negation. And negation. So basically, we have here propositional logic, right? To make it a temporal logic, we need temporal quantifiers. What are the interesting temporal quantifiers? Well, we are talking about the current state in, let's say, propositional logic. When we talk about time, we want to talk about the next state. So we have a next operator in the logic. If we have only a next operator, all we can say is quite boring, because then we can only talk about a few steps. By nesting, let's say if we nest 5 next, then we talk about 5 positions. Well, we want to talk about infinity, so we want to have something like an arbitrary. We want to point to some arbitrary point in the future. So that's what the until is for. So if you look at this form of syntax, it's not minimal. So there are different subsets of the operators that are minimal. Depending on the approach that we look at, we take different versions of LTL. This is kind of one that is kind of complete for what we're doing here. And you see here as well, for example, here we have the positive versions. Here we have the negative versions. So the dual of the until is the release. The dual of the next is the weak next. And then if we take these 2 lines, we can forget about the negation. So this is nice if you want to, when we want to put the formula into negation normal form. All right, so what is the semantics? I don't want to explain the semantics in detail. The idea is that we have our observation. I mean, that we have a trace, that we have an infinite word. So the infinite word is from sigma omega, so sigma is the alphabet, which is typically the power set of the atomic propositions. So in every state, certain propositions hold, like here, for example, P and Q hold, here only P holds, Q holds. And such a trace may be a model of a formula or may not. How is the model relation defined? Well, we define it by examples. P is satisfied. Why is P satisfied? Well, P is satisfied at the first position, so P is satisfied. Not P is therefore not satisfied. What about P until Q? Well, P until Q is satisfied. We have a row of P's until we have a Q. So there is a Q, and up to that moment P holds. Well, actually, it's much easier here because P already holds here. Q already holds here, so P until Q holds trivially. But next, P until Q also holds. We typically use abbreviations in the following way. Eventually, finally, phi holds. What does it mean? Phi holds at some point, and up to this moment, nothing special has to hold. True has to hold. True is always satisfied. So it only means that phi holds at some point. And what does globally phi mean? Globally means it is not the case that phi does not hold at some point. If it's not the case that phi does not hold at some point, then phi always holds. All right. So typical example that we are monitoring, it's never the case, it's always the case. It's always the case that both processes are not in the critical section at the same time. Or if we don't get an alive signal, then at least in the next step we get an alive signal. We skip that one. Another commercial here. LTL should be understood as a kind of assembler logic. So we have a very limited form of operators. And it's very nice to do a theory with a limited set of operators. You can give inductive proofs on the structure of the formulas. But of course, it's not that nice to specify or to use it in practical applications of larger size. For that, one needs syntactic sugar. One example is what we developed some years ago. I think it's not extremely good, but it may be a start, and it would be an interesting area in the neighboring fields of formal methods and software engineering to build high-level specification language with a solid foundational basis. Application specific driven, maybe domain specific versions of that, and then to compile it down to some kind of LTL version that then allows to be translated into monitors or maybe used into model checking as well. All right, so the idea here in runtime verification is that we specify correctness properties in LTL. That was the grammar that we used. And I need some further, And typically the truth is either the formula holds or it does not hold. But in the domain of runtime verification, as you learned this morning by Adrian, we also have the situation that the property is probably not satisfied right now. Yeah, so it may be not wrong, but it may also be not satisfied, maybe inconclusive. And for that, we have the notion of a truth domain, and the truth domain basically allows us to have several truth versions. And what can we understand by a truth domain? Well, it's a lattice. What is a lattice? Well, for any two elements, we have a greatest lower bound, which is the meet of two elements. We have the join of two elements. We work with finite lattices. We have a unique bottom and top element. Top is something like the best, it's true. The bottom is the worst, so this is false. We work with distributive lattices because we have distribution laws in typical Boolean logic, and we want to be able to use them as well. So we work with distributive laws, meaning when we take the meet of x and the join of y and z, we actually can take the join of x meets y and x meets z. And we want to have something like a negation. What is the idea of negation? Well, if we negate twice, then we are back to the very same element. So we want to have a dual of every element, and if we dualize twice, then it's the very same element. And we have this order. So false, for example, is worse than true. And if we negate true, it becomes false, and false becomes true. So this is the order changes, and we want to have this as well. All right, so we need in this talk 3 different kind of truth domains, and I would like to sketch them. Does everybody have the password? So we're working with B2. What is that? So we have 2 elements for the truth domain. So what is true? Well, we have the top element, we have the bottom element. Pardon? I have also black. Is that better? Better? Good. Okay. So we have top, which is basically true, and we have bottom, which is false. And yeah, if we negate bottom, it becomes true, and then it becomes false. All right. We add further truth domains later on. Okay, so the idea is that we have these kind of, I also denote the order, right? Top is greater than bottom. And the idea is that we use this kind of lattices, and basically, the sketch is a summary, but we will go through it for each individual version of the logics. If we have an arbitrary word W, and we consider the formula true, to which extent can we say this is true? Well, the truth value of this pair is top. Yeah? True is the best that we can hope for, while false always sucks. Right? So what about disjunction? I have a word W, and I want to check to which extent is phi upside true. Well, I check to which extent phi is true. I check to which extent psi is true. And OR means I take the best of it, which is in the lattice, it's the join of the 2 elements. And of course, if you remember, I mean, if this one is false, if this one is true, then it becomes true, right? So, and the join of the 2 elements, bottom and top, will become top. Yeah? So this is according to the intuition that we have. What do we do in negation? Well, we compute the truth value of W of phi with respect to W, and we take the dual element in our lattice. If a proposition P is in the first position of our word, it's fine. Otherwise, it's not so fine. Same with the dual. What about the other cases? Well, that is where our different interpretations of our temporal logic changes depending on the application area. And that is what we study now in detail. The first case is a simple case. So we have a program that is intended to compute a function, and it's intended to terminate. So we have a finite run. We start the procedure, it terminates. So given a specification along the computation, at the end we should be able to say true or false, right? So we have a finite word, and here is a dead end, and we have to say true or false. We had this generic definition for true, false, not, or, and atomic propositions, but the really interesting case is the next operator. And you might also think that the until cases are interesting, but actually they are not, but we come back to that later. So what is the idea of the next for a finite word? In the case that we know that the word is or represents a completed computation of our underlying system. Well, the next means I have to check phi starting from the next position. So I chop off the first letter, and starting from the second position, I just check phi. The interesting case now is what happens at the end. And those that are familiar with LTL and infinite words, there is not a big deal because an infinite word doesn't have an end. But if we have a finite word, it has an end. And what we follow here is the definition by Corneli and Manner. Well, at the end of the word, if there is no further position, we have lost. So what we understand the next is like an exist operator, like there exists the next position on which phi should hold. If there is no further position, we have lost. To have the dual interpretation as well, we have the weak next operator, which is next bar, and there it's the opposite. Yeah, at the end, it's fine. All right, so not a big deal. How can we build a monitor? Yeah, it's a finite word with a finite set of rules. You can write a program. I'm sure you can do that. But we will come to a more sophisticated idea later on. Now, if we are in the setting of online monitoring where we want to issue a verdict while the computation is still there, yeah, so we see the run to this moment, but we know that it's going to continue, but we just don't know how it is going to continue. It's not really a good idea to say either true or false, because true or false may depend on the next event that we see that we still don't know. And one of the ideas that also was mentioned by Adrian is that the semantics for runtime verification in the setting that we look at continuously expanding words should not go for true or false if the verdict may depend on the forthcoming future. And this is what we call impartiality. Such a semantic should be impartial. Go for the final verdict, true or false, only if you really know. Be a man, stick to your word. That's the idea. How can we do that? Well, obviously we cannot do that with two truth values. Yeah, if we have to say something like don't know. In the talk by Adrian, you saw, for example, don't know, this question mark. Here, for example, we go for 4 truth values. We say, well, it's presumably false. If we have the strong next operator and we have a finite word u and we are at the end of the position, if it's going to continue, then we will continue the evaluation of phi. But for the moment, if it really would stop, it would be false. So it's kind of false, but it depends on the future. So we say presumably false here. And of course a dual for the weak next operator. If we terminate, it would be true, it would be fine, but if we continue, we have to continue the evaluation. So we have a four element truth domain. And I call it V4. So we have top, we have bottom, and we have 2 values in between. How should I locate them? So how many lattices with 4 elements do you know? Yeah, of course you all know these, the Boolean lattice, right? True, bottom, something here, something there. But that's not the one that we are aiming for. We go for this one. Why? Because what would it mean? So we're not really sure for something. We're not really sure for some other stuff. Now, if we take the disjunctive combination, we would have to take the join of the 2 elements, meaning it would give us true. And that's not what we want. If we know that presumably we have lost, and in some other part of the formula, presumably we have won, and we want to take the best out of it, then the best should be this one, right? And this is why we go for this lattice. Is it really a truth domain? So we have to define the complement elements. So what should be the complement of true? If you shout it to me, then we are faster. And then, pardon? False, good. Dual or false? True, good. What about the other 2 elements? Exactly, yeah. You can check all the rules, it works. And it also gives us the right meaning. Now, how do we evaluate such a formula in this logic? Well, one of the interesting, or one of the typical requirements that we have for monitors is that we work from left to right. Why is that? Because we read the word step by step. If we have to go backwards, then we have to store the trace. And if we want to monitor for 3 days, then we have to store quite a lot, so we don't want to do that. We want to evaluate the trace from left to right, so in a one-way area. And how can we do that? Well, let's look at the different formulas. Evaluating an atomic proposition, seeing the current event is not a big deal, right? P either holds or it does not hold. Evaluate next formulas. Disjunction, conjunction is also easy, right? We can do that. The next formulas, well, we just wait for the next event and then continue. What about until? Until is cool because we have this unwinding rule. We have the recursion law for until. Phi until psi means either phi now, or if phi holds, then in the next position we continue with phi until verifying phi until psi. That means, considering the current position, if we have phi until psi to evaluate in the current position, we don't really have to do that. We have to evaluate psi in the current position, we have to look at phi in the current position, and we have to look at something starting from the next position. Yeah, so this is very easy to deal with phi until psi and with a dual, which is a release operator. So how can we do that? Well, let's look at the following Haskell style code. We want to evaluate in the force-valued semantics our finite LTL semantics, for example, the formula true by reading some letter A. Well, then this is top, right? True always gives top, false always gives bottom. Ignore the second component for the moment. And let's look at P. If P is in the set of the atomic propositions holding in the current position, then it's fine. If not, it's not so fine. What about the OR? Well, the idea of the OR was that we have to evaluate phi, we have to evaluate psi, and then we take the join of the two truth values. So we recursively apply our function on phi with the letter A, and the same with psi on the letter A. We get truth values, the value of phi, the value of psi, and we return the join. Yeah. Again, forget about the second component. Dual with the AND operation. Same with the negation. We compute the evaluation of the value of phi, and then we negate it. Until, as I said, very easy, right? We have to check phi until psi on A. Well, we have actually to check psi or phi and next phi until psi on A. So, not really a big deal. All right, so, but what about the next operator? The next operator, that's the interesting thing. Here we say, okay, we have to evaluate next phi, and we get the A. Well, if we stop, we have lost. If there is nothing else to come, then we have lost. So we return presumably false. But we have to remember that we have to continue the evaluation of phi starting from the next position. And that is why we return in our function a tuple. We return the current truth value and we return the formula that we have to verify starting from the next position. Yeah, so when you look at next phi, you have to verify phi starting from the next position. And for the moment, the current truth value is presumably false. And weakly next phi is actually the dual, right? So it's presumably true, but still you have to continue verifying phi. Now, because you get the formula that you have to verify starting from the next position, well, we have this nature in all the recursive calls, right? So when, for example, going back to this OR case, when we evaluate phi reading the current letter A, we will get the value of phi, but we will also get some formula that we have to continue to verify starting from the next position. So we get a rewritten version of phi, we get a rewritten version of psi, and that we have to verify starting from the next position on using a disjunctive combination of the two formulas, because why? Well, we had a disjunction here. And of course, if we have a conjunction, we continue with a conjunction. And if we have a negated phi, we continue with the negated version of psi. So the idea is, well, check what it's easy to check. Use recursive calls for the until use the unwinding rules, and for the next operators, just forget the current letter and continue with the formula. And in this way, we get a simple and easy formula. Well, this is considers letter by letter, so it's going from left to right. It's, in that sense, it's nice. Practically, of course, it's a little bit time-consuming to evaluate for each letter doing these kind of recursive calls. What do you do if you want to speed up computations, if you want to do pre-computations? There's a search algorithm by, I think it's Knuth Morris Pratt. You know that? What's the idea of this algorithm? It's substring. You look for a string in some large string. Yeah, what do you do? Basically, you build up an automaton. I think it's not really called in the description of this algorithm. But basically what they do is you build an automaton remembering what kind of information you've seen so far, and then you only have to do a lookup in an automaton table. So why not build an automaton-based approach for something like that? Well, actually, this is an automaton, what we have written here. Yeah. So what is the automaton-theoretic approach? Well, we synthesize an automaton, and monitoring is then only stepping through the automaton step by step. It's a lookup in a lookup table, which is much faster than doing this recursive computation. But basically, this is an automaton, right? Call this guy a state. Call this guy the input action. Call this guy the output action. And call this guy a state. Then this is a Moore or Mealy machine. Gerardo, come on. Moore or Mealy, 50% chance. Mealy, good. Pardon? Yeah. So it's a Mealy machine, yeah? We have an output for a certain transition. It doesn't really look immediately like a Mealy machine, but basically it's a Mealy machine. And you have to verify a little bit that the state space is finite and so on, but it is also easy to do. So basically this is a Mealy machine that we have written here. So one of the take-home messages, if you do runtime verification, build a nice, easy to understand recursive algorithm on that, and then try to look at it as an automaton and to speed it up. Yeah, you can do it like that. Actually, is it really an automaton? Yes, it's an automaton, but we do the conjunction of states here and the disjunction of states. So practically, it's an alternating Mealy machine. There are also Moore machines, but it's not a Moore machine. We come to Moore machines later on. It's an alternating Mealy machine. And you can translate that guy into a non-deterministic Mealy machine and the other one into a deterministic Mealy machine. And what is the blow up going from alternation to non-determinism? It's a term starting with E. Exponential, yes. And here's another exponential going from non-determinism to the deterministic machines. So it's a double exponential blow up if we want to go from alternating machines to deterministic ones. 5 minutes. Okay. But it's your choice whether you want to do this, to execute the alternating machine at runtime. Then, of course, it's slower, but the machine is smaller. Or if you want to determinize the machine, and then the verification is faster. All right. I skip that. Now, what about anticipation? That was missing in Adrian's talk. So what is anticipation? So impartiality, recall that. So impartiality means if the property is wrong, we are allowed to say wrong. Yeah, so what do? If you have an exam, if you're a student and you know that you should be impartial, what do you say to every question from your teacher? I don't know, right? Because then you don't say anything wrong. But you might understand that this is also not the best strategy to get the best mark, because we also want to say something that really, if we know something, we should also say something. So that's the idea, that we not just want to say don't know all the time, but we want to say something before. And that's where we come to LTL over infinite words in the setting of anticipation. The main motivation was that we wanted to use the existing semantics of LTL. And we do it in the following way. So we have a finite word u. That is what we have seen so far. We want to check whether phi holds. We want to know whether phi holds. We don't know the future. We don't know the extensions of u. So if all extensions, if for every infinite word sigma, when we extend it to u, phi holds, then we don't have to check, we don't have to continue monitoring anymore, right? If whatever future comes, we have 1, then we can go for true. If we have lost already, if whatever future comes, phi is violated, we can also stop monitoring and we can return false. There's no way to continue monitoring. In all other cases, it might make sense to continue monitoring, and we issue don't know. So impartiality, stay with true and false. Anticipatory, go for true and false, if you really know. Does it make a difference? Yes, take this very simple example, next, false. It's unlikely that we will win, right? But in the semantics I've presented you before, it will take 3 steps. Yeah, we chop off the first next, and we have to continue in the next state, and at some point we realize, oh, we have to verify false, that doesn't work, so we have lost. While when we consider the semantics already right from the beginning, if we haven't even started monitoring, we know that this formula, whatever we will see, it will violate that property, because this property is not even satisfiable, so we will return false immediately. So this is why the semantics gives us a more direct or more proper verdict faster. How does it work in general? I'm not sure whether I can really sketch that in 3 remaining minutes. So it works on the Bücher automaton. There is a very nice translation from LTL to Bücher automata. What is a Bücher automaton? This looks like a finite automaton. We are in some states. For example, we start in state 0, we reach some A, then we go to state 1. If it would be a finite state automaton, we could end here and would be accepted, but Bücher automata work on infinite traces, so we have recurrent states instead. And if you see, for example, this green light flashing infinitely often, then the word is accepted, and what you can easily see is, for example, that AB omega is accepted from this automaton. Very important is the emptiness test, because if you, for example, look at this guy, this area accepts strings, this one as well, and this one also. Now, if we look at the 3-valued semantics, what is important when we want to check a formula based on the translation into the Bücher automaton? Well, once we are in this area, for example, you see we cannot have an accepting run anymore. So once we are here, we have lost. If we are here, it's great, right? Whatever comes, we will see this state infinitely often, so we have won. The question mark area is basically this part, yeah, because it depends whether we continue here or whether we continue there. So basically, we have to analyze the Bücher automaton. What is the universal area? So in which part do we accept strings universally or words universally? In which areas do we have lost? And which is kind of the uncertain area? And how do we do that? Well, it's very easy to find the area where we have lost, but it's very difficult. Actually, it's p-space complete to find the area where the language accepted by the automaton is universal. But at least we know that this part should yield the verdict not bottom. It may be true, it may be don't know, but at least it should not be bottom. All right, and we can use this kind of analysis to get a partial answer. 2 minutes. And in this way, we can get a partial, we can answer whether for a finite string u, it's the result is bottom. And we can take the dual formula, translate it also into a Bücher automaton, do the very same analysis, and get the result for the other side. So we can check whether u should lead the verdict true, and in all the other cases we get to no. And then we can do whatever, translate it into finite automata, get a Moore machine out of that. And yeah, the complexity is double exponential, but it's optimal. It's cool, yeah? There are minimization algorithms for automata. And if you are not happy with the size of your automaton, and if somebody else finds a smaller one, then you immediately know the other one is wrong. Yeah? All right. Nevertheless, you have the choices to do certain parts on the fly in practice, and in this way limit the complexity of the practical approach. But if you want to have a deterministic monitor, this is minimal. All right, so there is the very interesting area of monitorable properties, but I think that Yliès is going to kill me if I continue. I should just show you one slide. This one. It's very important. If you look at the monitor, once you have lost, and you will lose forever because there is no continuation in which you can win. Same is for good. Yeah, in all the other states, the automaton outputs don't know. Now there is one special don't know state, and that is what we call the ugly state. And what is that? Well, the idea is that if you have a property like saying that it's always the case that at some point it gets better. Yeah, and this is not really monitorable. If it's bad today, you have not violated the specification because it can get better tomorrow. If it's good tomorrow, it's also fine, but maybe the day after it's bad again. So there are certain kind of properties that you will not be able to monitor at all. And you can see that from the minimal monitor. If you have this single state, once you enter that one and you will output don't know forever, then you're basically in the ugly situation. And you can also classify that in language theoretic terms. There is a notion of bad prefixes, good prefixes, and all this kind of stuff. And basically, the notion of monitorability from Prunelli and Sachs means that a property is monitorable if and only if there is no ugly state. That's a correspondence to that. I don't talk about the predictive semantics. I just want to show you that you remember this picture from the construction. You can also take into account the monitor together with the program. So far in the whole monitoring approach, we haven't really touched the program. But if we know a little bit of our program, we can perhaps optimize the whole monitoring process. And that's what also Wolfgang mentioned in the combination. So let me wrap up. We have different semantical versions of, let's say, for example, LTL, but of course for similar temporal logic as well. We can work on completed traces. We can work on non-completed traces. For non-completed traces, the notion of impartiality and anticipation come into the picture. If we want to combine that with the underlying system, we go for a predictive semantics. But that's clear, a definition-based, or all the definitions are according to the application areas, while we have to distinguish that from monitors. Monitors should work from left to right, and of course a monitor should yield the verdict according to the semantics of the underlying formula. And there is always a space trade-off. We can use rewriting techniques, easy to understand. We can translate it into alternating automaton that may increase, but then allow a faster monitoring stuff. LTL is just a very simple example. And there's lots of additional stuff to do, which is basically adding LTL with data, different semantics, real-time concurrency. In the morning you had cyber-physical systems, distributed systems that are concurrent and have real-time extensions. There's a bunch of different things to talk about, logging mechanisms that I don't go into. And there is a bunch of runtime verification frameworks. But let's go for the coffee break. Thanks.